Okay, so let's start. And we are going to continue with the same topic, analysis and design of beams for bending. So we are studying about shear forces and bending moments distribution along a beam. So last week, we discussed why it is important to know the shear force and bending moment, right? Because uh, as you now understand, once we apply a transverse load on a beam, the shear force and the bending moment, internal shear force and internal bending moment is not constant, right? Along the beam, the value is going to change. So in design point of view, designing the beam, what we need to know is the maximum shear force and the maximum bending moment. So therefore, we need to know where those values are on the beam, right? Maximum point, maximum shear force, where it is, and maximum bending moment, where it is, and the size of it. That is the reason we are learning about shear force distribution and bending moment distribution. So if I just show you the outline that I have used last week. So this is the second slide, okay, in my lecture note. The first I have introduced you different types of beams. So we learned about simply supported beams, cantilever beam, and then overhang beams, and also different types of loading, concentrated loads and distributed loads, right? And then I have introduced you one method, a simple method using basic concepts to develop a shear force and bending moment diagram. So that method, if you can still remember, we call it a method of section, right? So in the method of section, we take the beam and then cut the beam at a particular location and then draw a freebill diagram for that cut portion, right? Like this. And then we mark our internal or external forces, external reactive forces and external active force. Right? So in this case, it's a distributed load like this. And then the reactive force is the reaction force at the support. Right? And the distributed load, we normally represented or by a equivalent concentrated load, right? And after that, we apply our internal forces. So internally, we have the shear force V in the positive direction and the bending moment M, right? So in this method of section, so what we do, we use our equation of equilibriums and write a function for shear force and also function for bending moment. By looking at the shear force function and bending moment function, we can draw this shear force diagram and the bending moment diagram. So when we are finding this function, we need to find out these functions between discontinuities. Can you remember the discontinuities we talked about last time? So the load application points are the discontinuities because at that point, suddenly the shear force or bending moment going to vary. It is not going to continue, right? Therefore, the function for shear force, which is a function of x, right? And also the bending moment, m. We need to write these functions between discontinuities, right? So depending on the number of discontinuities, we have to write several equations. And using those equations, we can construct our shear force diagram and bending moment diagram. Okay, right. So today, I'm going to introduce you another method of constructing shear force and bending moment diagram. That is by looking at the relationship between among the loads, shear force, and the bending moment. Okay, so a new method. And after that, I will show you how to design a beam by finding out the maximum bending moment. And one more thing that we have learned last time, beams are normally going to fail due to bending moment. The normal stress resulting from bending moment is the most critical stress. So therefore, we are interested in finding maximum bending moment, right? So once you draw the bending moment diagram, you can find out the maximum values. And using that, using what we have learned 2 weeks before, that is about the bending formula, right? So we should be able to find out the bending stress. Using that stress, we should be able to design a beam so that it will not fail by the applied bending moment or internally generated bending moment, right? Okay, so before I introduce these two topics today, I would like to do one question with you, exercise with you, that will help us to revise what we have learned last week, right? So I'm going to use method of sections to draw a shear force and the bending moment diagram with an example. Okay, so we stopped last time in slide number 12. So today we are going to start with slide number 13. So now please go to the slide number 13, exercise 1. Okay, are you ready? Okay. Right, so first read the question together with me and then try to understand. Okay, so what it says, draw the shear and bending moment diagrams for the beam AB. Beam AB. The distributed load of 7,200 Newton meter extends over zero 0.3 meter of the beam from A to C. So A to C, applied load is a distributed uniform load, right? The size is 7,200 Newton per meter. That is the intensity of the load. And 1,800 Newton load is applied at E. So that is this load. So this is something new that we have not come across before. So always previously loads are applied directly on the beam. Now here the beam is AB and DE part is like an attachment onto the beam. So this load 1,800 Newton now applied on that attachment, right? So the effect of that load is felt by the beam AB. So we need to make use of that to now draw a shear force diagram and bending moment diagram for AB, beam AB, right? So the starting point is to draw a free body diagram, right? So it is what we do normally, first step, and then find out the unknown reaction forces using equation of equilibriums, right? Right, so let's do that first. So first, you need to draw a free body diagram. Now in this exercise, some of the parts are missing, right? So you need to write them down by yourself. I will write some of them, and others I will challenge you. Okay, you have to do it by yourself because as we develop the knowledge, understanding, you should be able to do it by yourself independently. Right. So the first diagram is the physical system that we have seen before in the exercise, and what is shown or drawn at the bottom is the FBD, free body diagram. And there you can see that I have marked the reaction force at A, which is a roller support, only vertical reaction force A, and at B it is a pinch joint. Therefore, we mark the X component and the Y component of the reaction. But by observation, you can say that this X component Bx is 0, right? Because there are no X direction external forces. Therefore, Bx is 0, right? And then the distributed load is now represented by or resultant or equivalent concentrated load The size of that load is 1600 Newton. 2160 Newton. So how it come about? You know how to get that one, right? Because this is equal to 7200, that is the intensity of the load, multiplied by the distance over which it is distributed. So it is 0.3. So you multiply this by 0.3, then you get 2160 Newton. And the location, application point here, it should pass through the centroid of the distribution. Distribution is a triangular distribution, sorry, rectangular distribution. Therefore, the load is applied right at the center, pass through the centroid of the rectangle. Okay, so the dimensions are given. And now the first step is to find out the reaction force at A and By. So shall we start? So in order to find out reaction force at By, at B, right, By, we need to apply equation of equilibrium. It is easy that we take the moment around point A. Sum of the moment at point A around point A should be equal to 0. Okay, so let's mark the positive direction as anti-clockwise direction. So now could you write the equation? So I'll write the equation and see whether you can write it by yourself as well. So I'll start with the reaction force By. Okay, By, and the moment around A, you need to multiply by the total distance, is 0.8 meters. And it is positive because it creates anti-clockwise moment. And then take 1800. So 1800 create clockwise moment, right? Therefore, it is negative 1800. And the distance 0.4 plus 0.15, 0.55. Okay, and then 2160 going to create again a clockwise moment, 60, and the distance is 0.15 equal to 0. Now you simplify this one and get this answer. You can check that. Okay, and similarly, can we write the moment around B, sum of moment around B, and then find the value of A. So if I first write A going to create clockwise moment, therefore it is negative A into the distance 0.8, right? And then 2160 going to create anti-clockwise moment, therefore positive. And then the distance 0.65 plus 1800 Newton. I put plus because it is also anti-clockwise direction. 1800 into 0.25 equal to 0. Okay, but you simplify this one, you get this answer. Okay, so yeah, you don't need to even write this one, right? Because we know that x direction, there are no external forces, therefore x direction component is 0. Now I have found the values of A and By by taking the drawing the freebird diagram for the whole system. Okay, but later we need to find out the shear force distribution and bending moment distribution for the beam AB. So therefore it is easy for us to mark all the external forces on the beam, right? But point E is not on the beam. So we can transfer the effect of load 1800 onto the beam AB. I hope that you have learned this one before in your prerequisite subject, right? So in fact, we can replace 1800 Newton with a force 1800 Newton at E, this one, or this is the load at E, we can replace it with a 1800 Newton force and 180 Newton meter couple at point D. So how you get that one? So let me show you some simple construction, then you will understand how it is done. Okay. So our focus point is now D. At this point, now I'm going to apply a force 1800 Newton, equal and opposite 1800 Newton. So did I do anything to the system? I didn't do anything to the system, right? Because they cancels off and still the system is in equilibrium. Okay, now you look at this 1800 Newton here and this 1800 Newton. So they together create a couple. Okay, so instead of showing the two forces, now I'm going to replace these two with a couple at point T. So let me erase this 1800 Newton now, and also just erase this one as well. Okay, and replace it with a couple. That couple is equal to 1800 into the distance between the line of actions of the two forces, right? So that value is 1800 Newton into the distance between the line of action of two forces. So maybe I mark that force again here. So line of actions, these are the two line of actions. So this is the distance I'm talking about. That distance is 0.1, 0.1. So that means this is equal to 180 Newton meter. So now can you see how I get this one? 1800 Newton couple plus 1800 Newton force at point D. So it is equivalent to the effect created by the concentrated force at point E, downward force. Okay, so this way we can now draw the free body diagram for AB. That is what I did in the next slide. So you can see that 1800 force now is applied at point D, and 180 Newton meter couple is there at the B as well, right? Okay, so now with this diagram, we can start writing our functions for shear force diagram and shear force and the bending moment. So we are going to use the method of section, right? So when you apply the method of section, you need to write the functions for shear force and the bending moment between discontinuities. Discontinuities are the load application points. Okay, so here, how many load application points? Now A to C load is continuous. Therefore, we can write one equation for shear force between A to C, and also one function for bending moment. But after C, suddenly there's no load. Therefore, the same function we can't use to develop shear force variation and bending moment variation between C and D. So for C and D, we have to write another two equations, right? Same thing happened at D because it's a load application point. So from D to B, again, we can represent the shear force and the bending moment using continuous functions. Okay, so by observation, you can say that now we have to write equations between AC, CD, and DB. Altogether, each one equation for shear force, one equation for bending moment, right? So altogether, 6 equations. Okay, let's use this method of section and write those shear force function and bending moment function. Right, so first I will use A to C, right? And then to write the equation, what we have to do, we have to cut the beam between A and C at any given point, right? Here, I'm going to cut it at point 1 and take the distance, or we can define our coordinate systems at 1. We measure the X direction positive this way, Y direction this way, right? This is Y, that's X. So the distance to the cut point here is X. Okay, so and then I take the part out, cut portion out, and draw the freeboard diagram. So what you see at the bottom is that freeboard diagram, right? From A, just mark the A here, and 1, right? So see how the external forces are marked. So we already found the reaction force at A, right? So it is marked there. And then the distributed load, we need to calculate the equivalent distributed load, that is equivalent concentrated load for that distributed load, right? So it is going to be equal to 7,200 into X. Okay, and then we mark our internal forces. So better you change the color of the internal shear force V and the bending moment M, just to indicate that they are internal forces. Okay. Okay. All right. Now write the equation of equilibrium for finding V and M functions. So we can first take the sum of forces in y direction, taking y direction positive like this. They add together equal to 0. Okay, now you can write with me faster. You know how to write that, right? So first the reaction force positive. Okay, and then the distributed load, the equivalent value of that is 7,200 into X is negative, and the shear force also negative. And also, can you remember that we mark this shear force here, V, in positive sense, according to the sign convention. Okay, right. So this is equal to 0. So once you rearrange that one, you can see that we can get a shear force function from A to C. So it defines the shear force variation. We can develop the shear force variation using this function. It's a linear function, right? Function of X. Right. So for the bending moment, we'll take the moment at point 1, right? Sum of moments at point 1, and add them all together. Once you add them together, it is equal to 0. So could you write the equation now? How about the reaction force 2,318? Is it positive or negative moment? I don't need to ask that question, right? Because you know that. So it's going to create a negative moment, right? Therefore, negative 2,318, and the distance is X. Okay, and 7,200 into X, that force going to create a positive moment. Okay, and like before, the line of action of the equivalent force going to pass through the centroid. Therefore, distance to that point from point 1 is X by 2. Okay, and the moment M is in positive direction, equal to 0. So once you rearrange the equation, you find that bending moment is a second order function. So it shows a parabolic variation, right? Parabolic function. Okay, so now we got two equations that defines the variation of shear force and bending moment between A and C. And these two equations are not valid between C and D. Therefore, we need to generate two other equations for C to D portion of the beam. For that, what we do, we cut the beam at any point between C and D. So I mark that point as 2 and draw the freeboard diagram below here. There, again, you can see all the external forces are marked first, and then we need to mark our internal shear force and internal bending moment. Okay, I can see a mistake here, right? So here, the load of 2160. It is applied right at the middle of the distribution, right? Therefore, this length here, previously how much? 0.3 meters. So therefore, this is 1.5 meters. Okay. Therefore, this length here, this one, should be x minus 0.15. So please correct that one. X minus 0.15. Okay, now all the details are there. So you can write your equation of equilibriums. So I first write my sum of forces in y direction, which is equal to 0. Okay, 2318 minus 2160 minus v equal to 0. Okay, so you get this equation. So it's a constant. So it says that shear force from C to D is a constant, right? Okay, and then take the moment at point 2. Sum of moments at point 2 is equal to 0. So there, first you can take 2318. It will create a negative moment, negative 2318. The distance is x plus 2160, right? And now the distance from point 1 to line of action of that force is x minus 0.15. Okay, right. And the last one is moment m equal to 0. So once you rearrange the equation, you get a function for bending moment m. So that one, that equation explains the shear bending moment variation from C to D. Okay, so now we can construct the two diagrams, shear force diagram and bending moment diagram between C and D using these two equations. And the last one is to define the equations between D and B. So I cut the beam at point 3. Always I measure the distance from point, right? So you can see I'm using X starting from A. So that way it is easy to construct our diagram. Okay, so now can you do this one now by yourself? I'll give you a few minutes, complete this one. And if somebody has done it, write the equation for me. Remember to change the color of this shear force and the bending moment, indicating that they are internal forces. First equation is quite easy, right? So you can write it easily. Just forces in y direction. 2318 minus 2160 minus 1800, okay, minus v equal to 0. Right. The second equation can be a bit tricky for you, so those who have not used to it, right? Those who have not learned it before. Right. So this one also will take the sum of moment in anti-clockwise direction as positive. So it should be equal to 0. So shall we write the equation starting from left to right? So start with the force 2318. So is it a negative moment or positive moment? I would like to have an answer from you so that I know that you understand it. Anybody? the reaction force 2318, it will create a negative moment about 0.3 or positive? Negative. Okay, correct. So it is negative 2318 and the distance is x. Yeah, correct. And then 2160, our equivalent concentrated load is going to create a positive moment, right? 2160 and the distance, again, this distance is 0.15, right? Therefore, it's x minus 0.15. Okay, and then we have 180 Newton meter couple, right? The moment. So is it a negative moment or positive? How come it's become a negative one? 2300. Oh yeah, that's so negative. Correct. You are writing the first one, right? Yes. The second one is positive. And now I'm asking about the bending moment 108, not the bending moment. I mean the moment 180 Newton meter. This one. So is it going to create a negative moment about 0.3, the cut point here, or positive moment? From the direction, you can tell that it's negative, right? So it is negative, remember, okay? So it's negative 180. And are you going to multiply by the distance? Yes or no? No, right? So because it is a moment itself, it's a moment, okay? So I'm not going to multiply by distance because I'm telling this one, I have observed this thing last year. Your previous, seniors, some of them multiplied by the distance. Okay, 180, and then we have 1,800, right? So it is a positive moment, 1,800, and the distance is x minus 0.45. Okay, and the last one is the internal bending moment m in positive direction equal to 0. Now you simplify this one and see whether you can get this equation, the solution, final solution. So it's a linear function, right? Okay, so now what we did actually, we have written 6 equations for shear, 3 equations for shear force and 3 equations for bending moment. Now let's construct our shear force and bending moment diagrams. So go to the next slide. There I have transferred these 6 equations. This is the equation number 1. Let us mark them, identify them by a number. 3, 4, 5, and 6. Okay, so by taking the equation number 1, now we can draw the shear force variation between A and C, right? So now by looking at the equation 1, what is the value of V when x equal to 0? When x is equal to 0, V is equal to 2,318. So now in the shear force diagram, so I mark x direction this way and y direction shear force. Okay, so let's mark the shear force on the y axis at x equal to 0. It is 2,318. 2,318 Newton. So can you see a relationship between these two now? The internal shear force is equal to the reaction force applied at that point, right? Okay, and then when x is equal to 0.3, that is at C, right? When X is equal to 0.3, what is the value of B? Can somebody do the calculation and tell me the answer? 158, correct. 158 Newton. So we'll mark that one in here. 158. Okay, 158 at that point. So in between, shear force variation should be linear, right? Because it's a function of X. So we can simply connect these 2 points now and get the shear force distribution. So it's a straight line. Okay, let me draw a straight line like this. It's a straight line. Okay, and then we'll focus on equation number 3. From equation number 3, we can develop the shear force variation from C to D. So it's a constant, right? 158. That means shear force remains the same from C to D. The reason is there are no external forces from C to D. Just before D, right? Just before D, not just after D. Just up to D. So this is the variation. And for D to B, we are going to use equation number 5. So equation number 5 says that, again, when X is equal, at point D, suddenly shear force become negative 1642, right? Because this equation valid from D to B. D just after D up to B, right? So that means the shear force suddenly jump up to negative 1642 just after D, right? Like this. So you can see that the discontinuity, right? The function is suddenly become discontinuous. And after that, it remains the same up to point P, negative 1642 Newton. So you compare it with this value. Again, you can see that the shear force at that point is equal to the reaction force at point B. Okay, now our shear force diagram is complete. The area under the curve is represented by these hash lines, the area marked as hash line with hash lines. Okay, right. Now let's develop the bending moment diagram. So for that, we are going to start with equation number 2. Right, equation number 2. We can start with X equal to 0. Right, when X is equal to 0, what is the M value? Is equal to 0. Okay, 0. So physically, when you look at the diagram in our physical system, also it is clear, right? Because at point A is a roller support. At a roller support, bending moment is 0. Okay, very intuitive. And then when X is equal to 0.3, what is the value of M? Check your answer again. 3714. It cannot be that big. I think 371.4, correct. 371.4 Newton meter. Okay, let's mark that one here. This value as 371.4 Newton meter. Right, now between A to C, the variation of the bending moment, is it linear or parabolic? Because it's a second order function, right? The second order function. Therefore, the variation is non-linear, parabolic. So can you draw? I'll try my best to draw a parabola like this. It's not linear. Okay, it's a parabolic function. So now can you see another pattern developing here? Because when the shear force is linear, variation is linear, or the slope is constant, you get that bending moment variation become parabolic. Or another word, you can say that the function is one order higher than the shear force function. Okay, right. Then go to equation number 4. There you can find out the M at point x equal 0.3. What's the value? So if you do the calculation, you again find that answer is same. Yeah, Newton meter, correct. Right. So same point. And then when x is equal to 0.45, right, at C, 3.45, M, what's the value of that? You simply substitute x equal to 0.45, yeah, 395.1. We'll forget about the 0.1, right? 395. Okay, Newton meter. So it's a bit higher than this one here, 395. So what is the variation? The function from C to D is a linear function. Therefore, it's a straight line, right? Like this, straight line. Remember, it's a straight line. Okay. And next, we are going to use equation number 6. And there again, we can find out this equation valid after D, from D to B only. Therefore, when x is equal to 0.45, what is the value of M? Yeah, so it's different, right? It's not 395, 575.1. Yeah, we'll write as 575. Thank you very much for doing the calculation for me. Okay, 575, maybe here, 575. Okay, and then what's the value of bending moment when x is equal to 0.8 m? By observation, I can tell the answer. But if you want, you can substitute the number 0.8 to the x and calculate the value of m, and it is equal to 0. Right? Just 0.4, right? Is almost equal to 0. Okay. So this is the value, 0.4. So in between, the bending moment variation is linear because it's a first order function. So we just connect these 2 points using a straight line. So this is the shear force variation from A to B. So the area under the curve is represented by this hash line, this area. So now can you find where the maximum bending moment is and the value of it? So that is what we are really after, right? We want to know which one, where is the maximum bending moment and the magnitude of that value. So if you know that, then we can find out the stress created by this bending moment, and then we can decide the right cross-sectional shape and right material for this beam, and we can design the beam. Right. So and also maybe you have noticed that when the shear force is constant, now in here shear force is constant, right? When the shear force is constant, your bending moment is linear. Bending moment variation is linear. So here also shear force is constant. Bending moment variation is linear. One order higher than the shear force function. So you can see that there's something emerging here. There's a relationship between the force applied and the shear force and the bending moment. Okay. Now, this method that we use up to now, the method of section, is really cumbersome and difficult when it comes to a complicated load case, beam with many different loads or many different discontinuities, right? In this case, we had to write 6 equations. Assume that there's another load, then what's going to happen? We have to write 8 equations, sometimes 10 equations, right? So as a method, it is very straightforward. The chance of you making mistakes is less. but it is time consuming, right? So practicing engineers in the industry, they, oh yeah, that's right. So they don't use this method that much. We can use this method for simple load cases. When the loads are complicated, so many different load types, then we need to have a much easier method. So that is what I'm going to introduce you today, right? So the second method of developing shear force and bending moment diagram. Now, up to now, this point, you mean the development of the shear force diagram and bending moment diagram using method of section. Now you should be able to do by yourself, right? So it's a lot of repetition of the same method, right? Equation of equilibriums. So we have done several questions so far, tutorial questions as well, right? So finally, and next week, Monday, also I will do some more questions. So up to this point, I'm going to test in the test. Okay, right. Now, let me now introduce the today's topic. Now we understand why we need to have another method, right? Another method because it is we need a simple method. Okay, so this simple method, or kind of simple, right, is developed by looking at the relationship between load, shear force, and bending moment. So if you understand those relationships, in fact, practically they are related, right? Why there are internal shear forces and bending moment? Because of the externally applied loads. So the size of the load and the nature of the load has an effect on shear force and bending moment. So if you understand that relationship, we should be able to construct this diagram faster. So if you know the loads, then we should be able to tell how the shear force is going to vary. And if you know the shear force variation, you should be able to tell how bending moment is going to vary, right, along the beam. So in fact, most important diagram here is the bending moment diagram. So we should be able to construct the bending moment diagram faster by looking at these relationships. Okay, that's what I'm going to now develop. So this can be somewhat complicated for those who don't have good experience, right, with the mathematics. So I'm going to go slow at the beginning, and then once you capture the concept, we will work faster. Okay, right. So far, any questions? I hope that the method we learned up to now, method of section, is straightforward, right? If you have any questions, still you cannot use the equation of equilibriums, please come to the face-to-face tutorial class next week. We can discuss and I can help you to understand those things. Okay, so without knowing how to write equation of equilibriums and developing the shear force function and bending moment function, you can't develop your bending moment diagram and the shear force diagram. Okay, those fundamentals you should know, right? So in order to develop this relationship between among, right, because there are three things: load, shear, and bending moment. I'm going to get a generic example, a beam which is loaded with a distributed load like this beam. And you can see the intensity of load distribution is not constant. It's going to vary from point to point. So I'm going to take a point, random point on this beam AB. That point is this C. Okay. And at that point, the intensity of the load applied is W at point C. Okay. And then I'll take another point, delta X, away from this point C, C prime. Okay. And then mark this one out and then draw a free body diagram for that cut portion. This is the FBD for this small section C to C prime. And see how we can draw our free body diagram here. So since the delta X is very small, and I said that at point C, intensity of the load is W, and at C prime also we can assume that it is still W. It may be a little bit higher or lower, but still we can, since delta X is very small, it is W, right? And therefore the load distribution is rectangular, and the equivalent load we can calculate as W into delta X, right? So we replace the distributed load with the equivalent force, and the distance to that point should be right at the middle of the rectangle. Therefore, it is delta X by 2 away from C prime, or even from C. And next, we are going to mark our internal shear force at point C, which is V, and internal bending moment M. And both of them are marked in positive sense. Okay, positive sense. And then the other side, shear force should be different and the bending moment should be different. So I mark it as V delta V, okay, yeah, and M delta M. So now this small portion C prime should be in equilibrium now, right? Okay, so for this portion, now we can use our equilibrium equation, and then develop a relationship between the shear force and the applied load. So see how I'm doing that. So I'm going to take the sum of forces in Y direction for the free body diagram, this one, the same one, okay, just transferred here. Okay, so by looking at the FBD, you can now say that shear force V is in the positive direction, therefore it is positive V, and V plus delta V is in the negative direction, negative. And next we have W delta X, the equivalent concentrated load. It is also in negative direction. Okay, so once you simplify, you get this equation. Delta V is equal to negative W delta X. So that means shear force variation between C and C minus is equal to negative W dx. W dx is in fact the area under this curve, right? So now we can say that between 2 points on the beam, shear force variation is equal to the area under the load curve. So that's what it mentioned here. Negative of that, right? Or another word in mathematics term, right? Okay. So let's divide this equation by delta X, and then let delta X approach to 0. So then we can find out the slope of the shear force variation, right? Shear force curve, and it is equal to negative W. So that means the slope of the shear force curve at a given point is equal to the intensity of the load at that point. If there's no load, then slope becomes 0. Okay, so now we extend this understanding to find out the shear force variation between 2 points from C to D. From C to C prime, shear force variation is equal to the area under the load curve, right? Then the shear force variation between C and D, also the area under the load curve, right? So you can obtain that one by integrating this function 1 between C and D. So then you get Vd minus Vc is equal to negative integration from C to D W dx. So that means this part is the area under the load curve. Okay, so we got a very simple relationship between the shear force variation and the load applied. So this equation is valid only between two concentrated load points, right? When the concentrated load point, at a concentrated load point, this equation is not valid. Why? at that point, as you observed in the previous example, if I go back to that example, you can see that here there's a concentrated load. Suddenly, you can see shear force become discontinued, right? So therefore, this equation is not valid at those concentrated load application points. So it is valid for distributed loads, and even if there are concentrated load between or with the distributed load, then again this is not valid. Okay, as long as the load is continuous, then this equation is valid. Okay, right. So now we got a relationship between the load and the shear force. Then we'll look at the bending moment. Okay, so we can get the relationship for the bending moment by again using the same free body diagram. Now we are going to get the sum of moment about point C prime here. Okay, C prime. So then we get m plus delta m at that point C prime. It is a positive moment, and m on point C is a negative moment. Okay, and then v, this v create a again negative moment, and the distance to that point is delta x, therefore negative v delta x, and then w delta x going to create a anti-clockwise moment, therefore it is positive. Okay, w delta x is the size of the load, and delta x by 2 is the distance to the point of a line of action of the force. Now it is equal to 0. So once you simplify the equation, you get this equation. So like we did before, just divide this equation by delta x and let that delta x approach to 0. Then we can find the slope of the bending moment curve at that point, at point C, right? dm over dx. And once you do the simplification, you find that that value is equal to v. So what does it mean? The slope of the bending moment curve at a given point is equal to the shear force at that point. So if you have already developed your shear force diagram, now you know the slope of the bending moment curve at that point. Okay, so move a little bit further by integrating this one between 2 points C and D, you should be able to find out the bending moment variation. That is MD minus MC. It is equal to integration from C to D V dx. That means V into dx is the area under the shear curve. So that's also very useful information. So once you complete your shear force diagram, you want to find out the bending moment variation between 2 points. That variation is equal to the area under the shear force curve between those 2 points. Right? Very good information. So once you develop your shear force diagram, now using this relationship, you should be able to construct your bending moment diagram without writing any equations. Right? But you need some practice, good understanding about these concepts. Okay, so we'll apply this one. And here, all the calculation steps are given, but I'm trying to use equations to relate what we learn, okay, with this concept. And later I'm going to, develop the 2 diagrams without writing even a single equation. Okay, right. So here we have a distributed load applied on a simply supported beam A to B. So say draw the shear and bending moment diagrams for the simply supported beam shown and determine the maximum value of the bending moment. So our target is to find out the maximum value of the bending moment. So starting point, again, always you need to find out the unknown reaction forces. Right? In this case, by observation, I can write the reaction force. I think you can do the same thing, right? because loads are uniformly distributed. Therefore, support reactions A and B going to be the same, and they are going to share the total load. Therefore, total load, if you mark the equivalent concentrated load, it should be W into L, right? And it is applied here from this point to this point, L by 2. That is right at the center. Maybe I change the color, L by 2. Right. So therefore, the load at A should be this WL divided by 2, because A and B going to share the workload. So this is the reaction force. You can find the same thing by writing equations, but here it is not necessary. Okay, right. Now we are going to draw the shear force diagram by looking at the load distribution. So now you can remember that this relationship, right? Shear force variation is equal to the negative of the area under shear force diagram. Right. So now I'm going to connect what I'm telling now with some equations. So we'll use the same method of section that we used before. So we'll cut the beam at point, let's say mark this one as 1. Okay, and the distance to this point is x. And if you draw the freeboard diagram, it would be like this one. So this is my reaction force RA, which is WL by 2. And then I am going to have a concentrated equivalent load. It is equal to W into X, right? Because this distance here is X, this is X. And then we have shear force V and the bending moment M. Okay, so if you want to find out the shear force V, we know the variation of shear force between point 1 and A, V minus VA should be equal to negative of the area under the load curve, this area. So that is W times X. Okay, W times X. So now V going to be now VA minus WX. So what is V? Previously we learned that shear force at point A is equal to the reaction force at that point. So it is WL over 2, right? So you can see that now I'm substituting VA here as WL over 2, and it is equal to RA. Okay, so after simplifying, I get this kind of equations with it's a function of X. So when X is equal to 0, shear force V is equal to WL by 2. That is the reaction force at point A, right? So that is what I marked in here, WL by 2. And now we'll find out the X shear force X when X is equal to L. Shear force V going to be negative WL by 2. Can you see that? I just simply substitute X equal to L, then you get this answer. So that is at point B, shear force is negative WL by 2. So in between is a linear function, therefore linear distribution like this. Okay, and it is obvious we don't need to do this calculation because we know that when the load is uniformly distributed, shear force going to vary linearly between the load application points. Okay, I forgot to mention very important thing in the previous slide. Let me go back. Oh no, here I didn't mention this one, right? So in this equation, dm over dx is equal to v. So let me write it again here. Dm over dx is equal to v. So what if dm over dx v equal to 0? Shear force is 0. When shear force is 0, the slope of the bending moment curve becomes 0. So in your mathematics, you should have learned that when the slope becomes 0, that means that is the maximum point or a minimum point. Right? So now we know that when shear force is equal to 0, those points are very important because those points tells me where the maximum bending moment is. So that's what is mentioned here. This equation also shows that V equals 0 at points where M is maximum. That is a good information for us, right? So once we draw the shear force diagram, by looking at the shear force variation, we can tell where the maximum bending moment is. When the shear forces become 0, bending moment is maximum. So we don't need to do a lot of calculations now, right? Construct your shear force diagram, and then you can immediately find out where the maximum bending moment is. That is what we are after, right? We don't need really the bending moment in other places, design point of view. Okay, right. So now here at this point, we can see that shear force is 0. Shear force is 0 means dm over dx is equal to 0 at that point, right? So it is going to happen when L is equal to L by 2. So here the slope, you can see it is 0. That's the maximum point. Okay, right. So now, in fact, we can construct this shear force bending moment diagram immediately by the relationship that we have learned before with this M here, right? The variation of this bending moment from point 1 to A is equal to M minus MA is equal to the area under the shear force diagram between those 2 points, right? So what is the area under this shear force diagram between the 2 points? So that is the area, right? Right. So let's use the equation given in here, and later I will show you how to find out the maximum bending moment using the area calculation. And here we already found that it is equal to this equation here. Okay, so we can replace this V by that function of X of shear force, and then after simplifying, you find that W is equal to this kind of equation. It's a second order function, right? So when X is equal to 0 here, M become 0. And when X is equal to L by 2, okay? So what is the value of M, which is now maximum? You can see once you substitute this X equal to L by 2, you get this answer, WL squared over 8. Okay, so this value. So you don't need to do this calculation to find out this one, right? In fact, this WL squared over 8 should be equal to this area. So you can see it in the next slide. So now this is the first one is the shear force diagram, SF diagram that we have just drawn, right? So now if the bending moment, if you know the bending moment at point A, this is MA. What is the bending moment there? Go back, and it's a simply supported beam. Therefore, at point A, bending moment is 0, right? So we know that by practice, right? Practical understanding. And then if you want to find out the bending moment variation from this point A to L by 2, this point, let's take that point as the maximum bending moment, that we know that maximum bending moment happens at V equals 0. Then that maximum bending moment minus MA should be equal to area under the shear force diagram. Okay, so that means this area. So this length here is L by 2. Height is half WL. So you can see that I calculate that one. The area of the triangle is half base L by 2 into height WL by 2. Okay, half base into height WL squared over 8. So without doing any integration and all the calculation, we can find out this value. Okay, so finally, now we learned that we should be able to sketch the shear and bending moment diagrams without actually determining the functions of Vx and Mx. Okay, so we can do that one if you know the initial values of few bending moment at few locations. Normally we know the bending moment at few locations from practical experience. Okay, let's apply this understanding immediately for example, and then we know how to use it. And after that, we can have a short break. Okay, so just to continue with what we have just learned, let's do this example as well. So this is a concept application. So I have written all the steps for you. I just want you to understand what I have done. That's it. Okay, so now by looking at this beam, we need to now draw the shear and bending moment diagrams. It's a kind of a complicated situation here. Why it is complicated? Now, by looking at the way the loads are applied, can you see how many discontinuities are there? Discontinuities are the load application points or reaction points, right? So A, B, C, D, and E, they are all the points of discontinuities. Therefore, if you use our first method of section, right, then we have to write functions from A to B, B to C, C to D, and D to E. 1, 2, 3, 4. We have to write 8 functions. Time consuming. So now let's try to do this thing using the new method that we have just learned. Whatever the method that we are going to use, the first step is to draw the freebird diagram for the entire beam and then find out unknown reaction forces. Okay, so you go to the next slide, then there you can see that how I'm drawing the free body diagram. Mark the reaction force at A and at point D. D is D, AY and AX, and by observation I can say that this AX is equal to 0. Okay, now you should be able to write the equation of equilibriums and then get the answer for A, Y, and D. So the calculation is there. I'm not going to go through that one. You know how to do that now, right? But better that you mark my direction of the positive moment. Okay, the answer is 117. So that's what I marked in here, right? And then positive Y direction this way. Okay, so then AY become 81 kilonewton. Okay, now let's try to draw the shear force diagram directly without writing any equations. Okay, so now you can see that from A to B, there are no other loads, right? And first establish the shear force at point A. So previously we saw that the shear force at the point of reaction is equal to the reaction force. So at point A, shear force is 81 kilonewton. Right? Immediately we can tell that. So if you have any doubt how it come about, you can simply cut this beam between A and B, any point here, and draw your free body diagram and write your equation of equilibrium and find out the V inside. Because A to B, V is the same, right? So it is 81. You get the positive value for that. Okay. So do I need to write that one? I hope that I don't need to write, right? So you can write your, draw your free body diagram and get this value. And up to B minus, I say B minus means just before B, shear force is constant 81. Okay. And just after B, that is B plus, shear force may not be the same because now 90 kilonewton comes into our free body diagram, our portion of the beam that we are going to consider. So if you want to find out exactly what that shear force at that point B and C, you have to cut the beam at a particular location. Here I have cut the beam at 1, and just to make sure that you understand it, I have drawn the the free body diagram for that cut portion and mark the shear force V and the bending moment M. Okay, so if you want now, you can write a free body, the equation of equilibrium and find out the value of V. But I don't need to write now, right? By observation, I can directly write it. So I want you to develop the same skill now. Okay, so V is downwards, 81 is upwards, right? Therefore, I can say V is equal to 81 and the 90, negative 90. So here, let's say mark this one as V1. Therefore, V1 here is equal to 81 minus 90, that is minus 9 kilonewton. That means just after B, shear force become minus 9. Sudden change, discontinuity, right? Sudden change, minus 9. And it remains the same up to point C, C minus, just up to C, right? And at C, if you want to find out the shear force, you need to cut the beam between C and D. Now you can imagine it in your head and directly write what that value is. Let's say that point is 2. Then what is the V2? We can write V2 by observing the cut portion. See whether you can write it with me. V2 is equal to 81 minus 90 minus 54. Right. So that is minus 63. That is what happened to the shear force just after C, minus 63, go down. And then from C to D, no other forces, therefore shear force remain constant up to point D, D minus. Okay. At D, what's going to happen? Suddenly there's another force, right? Let's say I'll take just after D, D plus, maybe at this point 3. Very small portion of the member after D. So then we can neglect the distributed load, because compared with the distributed load, there's no load at all. Or we can replace the distributed load by a equivalent force, right? Then what comes to the calculation is shear reaction force 81, 117, and the applied loads 90 and 54. Therefore, V3 is equal to what? Plus 81 minus 90 minus 54 plus 117. Simplify this one. Answer is 54 kilonewton, and it is a positive value. And at point D, suddenly D plus, just after D, it becomes 54. Okay. Now from D to E, there's a distributed load. For when the distributed load is constant, so what's going to happen to the shear force variation? Is going to be linear, right? So one order higher. And also on a free end shear force, we know that it is 0. No shear force at free end E. So between the 2 points, it's going to vary linearly. Okay, so that is how we construct shear force diagram faster. Now, next we can construct our bending moment diagram by using the shear force diagram without writing any equations. If you know the area under shear force diagram at different portions of the shear force diagram, then we can construct our shear bending moment diagram. So for that, I need to calculate the area under this portion and up to this point, something like that. So I calculated the area here, 81 into 1.8 meters, then it is become 145.8. And this area is above the x-axis, therefore we take as positive area. Okay, and the area below here, it is minus 9 into 2.4, this minus 21.6, and we take this one as a negative area below x-axis, therefore negative 21.6. So likewise, we can keep on calculating the area. So the calculated areas are given in the brackets. Okay, let's move to the next slide. So I have moved the same shear force diagram, and now I have constructed the bending moment diagram. So to construct the bending moment diagram, what we need maybe the initial bending moment. If you know key points bending moments, then we can construct the remaining shear force points, I mean the distributions, easily. Now, from point A is a simply supported point, right? Therefore, at that point, there's only reaction force, no bending moment. Bending moment is 0. So this is MA. MA is 0, right? And next, the bending moment between A and B, the variation, that is MB minus MA, should be equal to this area. Okay, so I'm writing that equation here. MB minus MA is equal to plus 145.8. And here we just found that MA is equal to 0. Right? Therefore, MB is equal to 145.8. So I mark that point. And in between, bending moment variation now is one order higher than shear force variation. Shear force is constant. Therefore, the bending moment variation is linear. Okay. And then from B to C, bending moment variation is MC minus MB. And that value should be equal to the area under this shear force curve here, negative 21.6. Okay. And here MB, we already calculated here, right? So we can simply substitute that value here. And then you get this answer. MC is equal to 124.2. So little below 145.8. In between, again, the variation is linear, right? Like this. Okay. Between C and D, MD minus MC should be equal to this area, 189, negative again. Okay. And then after substituting the MC value from here to this equation, we can find out MD is negative 64.8. Again, the variation should be linear like this. Okay. Right. So then from ME to D, ME minus MD should be equal to this area. Yeah, it should be positive 64.8. Oh, there's a mistake here. Again, correct this one. Okay, it should not be negative. It should be positive 64.8. Okay, and again, after substituting the value of MD in here, you find that ME is equal to 0. You don't need to do this one because we know that on the free end, bending moment is 0. So in between, what is the variation? Because we can look at the shear force variation, it is linear. Therefore, bending moment variation is one order higher. That is a parabolic variation like this. If you want to know the shape, why this shape is, you can simply take the dm over dx at key points. It should be equal to v, right? So now you know that at point E, dm over dx, v is equal to 0. That means the slope of the bending moment curve should be 0 at that point. So you can you see it is 0 when you draw it that? So that is why the shape is like that, not like this. Okay, so it's not like that. Okay, all right. So I hope that we have learned something new today. Okay, using this method, you can construct your shear force and bending moment diagrams faster, but you need a bit of practice. Okay, right. So let's have a short break now. Now it is 5:04. We'll start at 5:15. Okay. So if you have any questions or anything that you don't understand up to now, you can ask those things, or else have a short refreshing time and come back. Okay. And please mark your attendance if you have not marked that. And don't run away after marking attendance. Attendance will not give you knowledge. Okay. Right. Okay, right. Shall we start? Hope that you're back after the break. So I'm going to do another exercise with you. Now, this one maybe some parts are missing, so you have to construct by yourself, do by yourself. Okay. So you need to, let me see. No, it is done right for you. Right. Because it's a different kind of questions. Um, Now, for this exercise, we are going to use new method that we just learned. That is developing the shear force and bending moment diagram using the knowledge of the the relationship between or among shear force, bending moment, and the load curve. Okay, so what we need to do, we need to sketch the shear and bending moment diagrams for the cantilever beam and loading shown. Normal approach is to first draw a freebull diagram for the whole system and then find out the unknown reactions. For this question, we really don't need to find the unknown reaction because reactions are at point C. So if you take a use the method of section also, right? You normally cut the beam at any point between A and B because it's the from A to B load is continuous. Therefore, at B there's a discontinuity, and then draw a freebull diagram. So without knowing the reaction forces, we can draw the freebull diagram and find out the internal shear force and bending moment, right? So therefore, here as our usual practice, we don't need to find out the reaction forces at point C. So let's use the method that we have just learned and with using our practical experience as well. How we construct our shear force and bending moment diagram. First, we need to know shear force or bending moment at few known locations. And then we look at the shape of the load curves or how the loads are applied. And then we can construct our shear force diagram. Right? Now here, at point A here, point A, there's no reaction force, right? Therefore, at this free end, shear force is 0. So that's the first observation that I can make. Shear force is 0. Okay, so you can mark that shear force 0 on the shear force diagram. And then from A to B, we know that shear force is continuous. The function is continuous, right? And then we should be able to find out the shear force variation from A to B by calculating the area under the load curve. So what is the area under this load curve? This is the curve, right? This is the curve, and area under this curve A is equal to half the base A into height W. Therefore, now we can write VB minus VA. VB minus VA is negative of the area under the load curve. So this is the area under the load curve, negative of it. Right. So now here we know that VA is equal to 0. This is 0. Therefore, we can quickly find out VB. So once we find the VB, you mark the VB on the diagram. So we found the 2 points, A and B shear forces. So in between, the shear force variation should be, you should be able to find out that one by looking at the load variation. Load is going to vary linearly. Therefore, shear force variation should be 1 order higher than that. It's parabolic. Right? So we can simply connect the 2 points with the parabolic curve. And if you want to find out exact shape of the curve, why it is like this or why not the other way around, you can find out the slope of the curve at point B. At point B, you can see just after B, there's no load. Okay, therefore, we know that dV over dx is equal to the load, negative of load at that point, and it is 0. So we can see that now at this point, the slope is 0. That is the reason why it has this kind of shape. Okay, And from B to C, no other loads up to C. Just up at C, there's a reaction force, but C minus, just up to C, there's no other load. Therefore, shear force remains the same value. So shear force diagram is complete, very fast. Okay, and next we need to find out we have to construct the bending moment diagram. So to construct the bending moment diagram, you need the area under shear force curve. So shear force curve has two portions here. So this is the first portion. So what is the area of this portion? It's a parabolic curve, right? So under the parabolic arc, the area under that one is given by this equation here. So if I write it here, A should be 2/3 of B into H. Here B is the width or the base, right? Base. This is the base. And next is the height. This is the height. So knowing those two, now we should be able to find out the area, this area here. Area A should be equal to 2/3 of B. B is A, right? And then height H. H is half WOA. Okay, so once you simplify this one, you can find that it is equal to 1/3 of WOA squared. But it's below x-axis, so it's a negative area, right? So that is why there's a negative sign here. That's the area. And next we need the area for the rectangular portion here. It is EC minus half WOA into this length, this L minus A. Okay, so then we get again negative area. So we know the areas of two portions, and now we can construct our bending moment diagram using these values. So let's go to the next slide. I have simply transferred the same information to here, the shear force diagram. And first thing that we need to now find out bending moment at some key points. So by observation, we can say that point A is a free end. There won't be any bending moment. Maximum bending moment going to be here. Here, bending moment is 0 at point A. So we first mark the bending moment at A, MA. It is equal to 0. And next, since A to B, the function going to be continuous. Therefore, we can find out the variation of bending moment between A and B, MB minus MA. It should be equal to the area under the curve of shear force. So that is what we can see here. And now we know that MA is 0. Therefore, we can find out MB. Right. So once you find the MB, you can mark that value. It's a negative value in here. MB. Right. So this is a parabolic curve, right? Parabola. Therefore, the variation of bending moment between A and B should be one order higher, third order function. So this is cubic function. It's a cubic function. Okay, so it's non-linear. And again, if you want, you can find out the shape of the curve, by finding the dm over dx at point 0, at point A. Because dm over dx should be equal to v, right? At that point, shear force is 0. That means dm over dx, the slope of the curve at that point is equal to 0. Right? So you can see that here, if you draw the slope, it is 0. Okay, so that is why this shape like this up to that point is a cubic function. And after that, from B to C, you write MC minus MB, it should be equal to this area, right? And then we can substitute the value of MB here. Then we can find out MC. So MC is a negative higher value than the previous one, 1 over 3. Therefore, like in here, right? Not here. And by looking at the shear force diagram, where the variation is constant, no variation, the bending moment variation should be linear. So we mark the two, connect the 2 points with a straight line. So it is linear. So now you know how to construct shear force diagram and bending moment diagram faster by using the relationships, okay, among those quantities. Okay, any questions? We'll do one more question and something in the different type of question. So then we are tackling different kinds of questions so that you get better understanding about different load cases. Okay, the next question is not done for you. So you'll write down everything by as I write, okay? So it's a very different kind of loading. A moment at point D, at point B, the size of that is T applied in anti-clockwise direction. The simple beam AC is loaded by a couple of moment T applied at point B. Draw the shear and bending moment diagrams of the beam. Shear force and bending moment diagram. Okay, so we'll write the solution for this one. Solution. What is the first step? You see whether we need the reaction forces. In this case, we need the reaction force, right? So first thing, we need to find support reactions. So for that, we need to draw a Freiburg diagram. So here, I'm not going to draw a separate Freiburg diagram. I just mark the reaction force at A and C. They are pin joints. Therefore, reaction force going to be a concentrated support like this. So we'll mark this one as RA and this one as RC. Okay. So can you find out RA and RC? We'll first find out the RA. I don't think we need RC. Okay. So we'll take the moment about C. About C. Sum of moment about C, MC should be equal to 0. Okay. So that means negative RA into the distance L plus, why I'm using plus, you understand, right? Because T is in the anti-clockwise direction. It's the moment T should be equal to 0. Okay, so this implies that RA is equal to T by L. So the direction I marked for RA is correct. T by L, positive direction. Okay, so now can we draw the shear force diagram? Right. So if you want to connect with what we have learned at the beginning, that is method of section, you can simply cut the beam between AB and BZ and calculate what the internal shear force V is. But for me now, with the new method that we have learned, we don't need that. By observation, we can tell what is the size of that shear force. So I'm going to extend these lines here because I want to draw the shear force and bending moment diagram just below the diagram. Okay, so first we'll mark the shear force variation. This is V, and then we have our X direction this way. Okay, there are few key points, A here and B and then C. So what is the shear force at point A? Is equal to the reaction force at that point, right? So I'll mark that point here. Is equal to RA, is equal to T by L. So from A to B, shear force should be the same, right? No other forces. T by L is a straight line like this, constant. And how about the B to C? You cut the beam at any point here and then draw a figure diagram and see what is the, let's say this is point 2. Right? So what is the shear force inside? Again, you will find that because T is not going to contribute for shear force, it creates a bending moment only, right? Still, shear force is T over L. So in fact, this shear force remains same. I'm going to draw a straight line to show the shear force variation. So shear force is the same from A to C. So even though there's a midpoint or at point B, there's a bending moment, or not a bending moment, bending couple, there won't be any shear force generated. Okay, it's like a pure bending case. Can you remember pure bending case? Inside, once you apply the pure bending loads, there won't be any shear forces, only resistive bending moment. Okay, right. So this is the shear force diagram. Okay, now by looking at this shear force diagram, you should be able to construct bending moment diagram. Okay, so let me draw the bending moment variation. X, and this way it is M. Right. So in order to construct the shear force diagram, we need the area under, to construct bending moment diagram, we need the area under shear force diagram and also known values of bending moment at key points. Right. And here at point A, what is the bending moment? Right. At A, bending moment MA is equal to 0, right? So there's no bending moment. So the starting point here is 0. And then from A to B, we can find out the bending moment just before B, right? A to B. We can find out the bending moment by taking the area under the curve of shear force. So how to do that? So we can write for bending, or we can say that I will erase this one. Moment at B. We are going to find out bending moment at B just before B, just before B. So MB minus MA should be equal to the area under the bending moment diagram. So I can write MB minus MA should be equal to area under the shear force diagram. So what is that value? TL into A, right? TL into A. So this is MB minus MA. And we learned that MA is 0. Therefore, MB is equal to TA over L. So we found the value of bending moment at this point. It is TA over L. And in between, bending moment variation is linear because shear force variation is constant. No shear force variation. Okay. And next, we'll find out the bending moment between B and C, or just after B. Bending moment just after B. Just after B. How to find out that? So maybe we'll use our knowledge about the method of section. We just cut this beam just after B, right? And draw a freeboard diagram. I'm going to draw a freeboard diagram because this is a new concept. So I want to draw a freeboard diagram and understand how it works. Okay. Here, and if this point I cut is 1, this is 1. So this is just after B. So B is here, right? This is B. So at the point of A, we have our reaction force RA. Just after B, now the couple T, this T, going to come into our freeboard diagram, right? So I'm going to mark that one here. This is T. Okay. And after that, we have our shear force again marked in the first view sense, and the bending moment M. So this is V1, this is M1. So we can say, yeah, M1. M1 is just after B, okay? So can you find out the value of that? The M1. For that, we need to write or take the sum of moments about M, about B. MB. You can say MB plus just after B, okay? Should be equal to 0. So can you write the equation? M1 plus T is in the same direction, right? And RA is in the negative direction. Our size of the RA is T over L into the distance is A, should be equal to 0. So now if you simplify this one, you can find out the M1 is equal to, I did the calculation, this negative T 1 minus A over L. Okay. So we found the bending moment just after B. So let's mark that one. Just after B, somewhere here. Okay. And the value is, don't have space to write that one. Maybe I'll write somewhere here. Negative T 1 minus A over L. So that is the bending moment at this point. Okay. And then what is the bending moment at point C? Again, at point C, bending moment is 0, right? So I can mark that bending moment directly at point C. In between, shear force vary linearly. Okay, sorry, shear force is constant. Therefore, bending moment should vary linearly. So I just connect these 2 points, then I get the shear force bending moment variation. Right. So at this point, suddenly jump down here up to this value. This is the area under bending moment curve. So we have developed the shear force diagram and bending moment diagram for this load case. So can you see some special pattern here? When there are no concentrated loads between 2 points, shear force always constant, same shear force. Right? Bending moment can vary. But when there's a torque or moment only between 2 points, shear force remains constant. Right? And the bending moment suddenly going to change at the point of load application. So the bending moment curve becomes discontinuous at moments. And the shear force diagram going to be discontinuous at concentrated loads. Okay, so another pattern that we can observe. So this kind of patterns, by making use of them, we can construct shear force and bending moment diagrams faster. Okay, right. So with that understanding, so we have done now several examples. So we'll go to some practical sites now. We'll do another question exercise. Here, our target is to find out maximum normal stress due to bending. So it's another thing. Up to now, what we did, we find out the bending moment diagram, and we developed the bending moment diagram and shear force diagram. So now we are going to extend our understanding to find out maximum normal stress due to bending by looking at all the loads and then how the shear force and bending moment developed. Okay, so here we have a timber beam and the loads are given. The cross section of the member also given. So this is the cross section. Width is 80 and the height is 250. So this is H and this is B. Okay, as we are going to find out the maximum normal stress due to bending, now we need to connect our knowledge about bending stress, right? Bending formula. Can you remember the bending formula? So sigma, if there's only bending is present, sigma is equal to negative my I. So bending stress going to vary linearly, right? And the maximum bending stress going to be at the outer surface of the member. And you know what the value of I? I is the moment of inertia of the cross section, and Y is the distance to any point from the neutral axis. So at that point, bending stress is given by sigma negative my I. But we are now interested in maximum normal stress. So maximum stress sigma m as a magnitude we write as mc over I, right? Here C, this one, is the distance to the outer fibers from the neutral axis. Okay, and this m then should be the maximum bending moment between A to D in this beam, right? So at any point, if you take, the bending moment is different. So if you want to find out the absolute maximum bending stress in this beam, then we need to find out the location where the maximum bending moment is. At that point, outer surface stress is the maximum. Okay, so this M here should be M max, maximum bending moment, the bending moment diagram. So now you will see that why we need to draw the bending moment diagram. And also now we are connecting our understanding about stress, bending stress, and the knowledge of bending moment variation, and tackle a practical problem, how to design this one. Okay, still I'm not designing, I'm calculating the bending stress, maximum stress. Okay, the starting point again, we start with the calculation of the, or drawing the free body diagram, and then calculating the unknown reactions. Okay, so how to do that? So can you do the calculation? I think now you can do it by yourself. Maybe I will guide you through a little bit. Okay, so let me draw the, I'm lazy to draw, right? So I'm going to get this diagram here. You can also want to get it, or you can draw it, right? Okay, so I got it. Right, so in fact, the reaction force at B, RB, already calculated here, and answer is given, and this is RD. So how to find out those two values? You know that, right? So you first write the moment balance, sum of moments around B, summation of all the moments should be equal to 0. Using this equation, you should be able to find out RD. The answer I got is 14 kilonewton. 14 kilonewton. And to find out the RB, you take the moment at point D. Oh, no need to do that, right? You can simply take the sum of forces in y direction. From this one, you should be able to find out RB. Value is 46 kilonewton. So you do that calculation. I know that you can do it now. Okay. So knowing those two, then we can simply draw our shear force diagram and bending moment diagram. Just to guide you through a little bit, okay. We'll connect with the knowledge of our method of section. Okay, and then we'll find out what is the shear force from A to B. Can you tell that directly now? What is the shear force from A to B? Because there are no forces other than the reaction force at A. Therefore, shear force should be equal to reaction force. But here I would like to cut the beam at 1 and draw a free body diagram for that part. This is A to 1. So what are the forces? Reaction force 20 kilonewton, and then no other forces. Shear force V, let's say V1, and the bending moment M1. They are internal shear force and internal bending moment. So find out the internal shear force now by taking the sum of forces at point 1 Fy, or not, for the whole free body diagram. So there are two forces, negative 20 and negative V1 is equal to 0. So this implies that shear force at point 1 V1 is equal to negative 20 kilonewton. So I just did this calculation to show you that here shear force is negative. The direction that I marked is wrong. But normally unknown shear forces we mark with positive sense, right? Okay, so how about the now shear force from A to B is constant. It is negative V1, that is negative 20 kilonewton. How about at point 3? What the shear force? Can you now directly write that one? V3 should be equal to negative 20 plus 46. Correct? Just after B, 46 come into the equation. Right, 46 is in the positive direction, 20 is in negative direction. Okay, right. So then once you simplify this one, you get the V3 value. It is plus 26 kilonewton. And how about 0.5? Because shear force from B to C is constant, 26. V5, can you write it directly now? There are three forces now, 20, 46, 40. Therefore, V5 is negative 20, positive 46, and negative 40. So if you simplify this one, you can find out V5 is negative 14 kilonewton. Okay, I hope that you understand what I'm doing here. Now I'm experienced, so I can write my shear force faster. Okay, right. So knowing those shear forces between AB, BC, and CD, now I can construct my shear force diagram. So it is what I'm going to do next. Okay, so can I move on? Okay, so I have constructed my shear force diagram. So from A to B, it is negative 20 kilonewtons, right? So this is the negative 20 kilonewtons. B to C, 26 kilonewton positive. And C to D, it is negative 14 kilonewtons. Okay, right. So now I need to find out the maximum bending moment. I can construct the bending moment diagram, or even without constructing the bending moment diagram, I can tell what it is. Right? But we'll construct the bending moment diagram. So I have done it here. I just want to show you how I did the construction here. So from at point A here, when x equal to 0, bending moment is 0, right? MA is equal to 0, no bending moment. I got 1 point. And then the variation of bending moment between B and A is given by this area. MB minus MA is equal to that area. MA is 0, therefore MB is equal to the area directly. So that area I calculated as minus 50. How it come about? This is negative 20 into the distance is 2.5. Right? I got that value. And then at point C. So we can draw this variation as a linear curve because constant shear force. At point C, what is the shear force? Sorry, bending moment. For that, I need to take MC minus MB. I know that MB is minus 50. Right. So would you like to write that equation? How I get this one? This is MC minus MB. It should be equal to this area here. It is 26 into 3. Okay, and MB is negative 50. Fine. So therefore, I can find out MC. You calculate the value, you will get it as 28. So that is how I got this value here. I mark that point. So in between, bending moment variation is linear, like this. Okay, and the last point, that is point D, shear bending moment is 0 and shear force variation is constant, no variation. So therefore, this should be a linear curve too. So that is how we construct bending moment diagram now. Okay, and by observation, now you can see that the maximum bending moment is in here, and its value is negative 50 kilonewton meter. And the maximum shear force is this value, 26 kilonewton. So that's what I mentioned here. Maximum shear force 26 kilonewton. Maximum bending moment happens at point B. The magnitude of that bending moment is 50 kilonewton meter. Okay, right. Now knowing the maximum bending moment, now I can use my bending formula. Okay, sigma m is equal to maximum bending moment into C over I. Okay, here maximum bending moment M is now at MB, right? And C over I. Or I can write in terms of section modulus. Here section modulus S is equal to I over C. Section modulus I over C. Right. So if you know this section modulus, then I can find out the maximum bending moment because I already know this value. Okay, so only thing is I don't know what this S is. So let's see the relationship for S in terms, because S is a geometric property. It relates to the geometry of the cross section. Here the cross section is given as a square or rectangular section like this, right? And its width B is given as 80 millimeters, and the height H is given as 250 millimeters. I'm going to have a quick look at it because 250 and 80 H and B. Okay, and this member cross section going to bend about the neutral axis. So this is the neutral axis. Okay, neutral axis is going to pass through the centroid here. Okay, and therefore the distance to the outer fibers from the neutral axis is given here, C. That C, what is the value of C? C should be equal to H by 2, correct? It is H by 2. So now can we write what this S is? S is equal to I. What is the I of this cross section in terms of H and B? We already learned that, right? Write it in here. S is equal to 1 over 12. That is I. Okay. B into H cube. That is the moment of inertia of the rectangular cross section divided by the C. C is H by 2. H by 2. So you simplify this one, then we can find out the value of S in terms of B and H. It is BH squared over 6. So this is S. This doesn't look like S, right? S. So this is how we find out the relationship of S in terms of width and the height of this section. So now I can write this S here as BH squared over 6. So what is the value of B? B is 80 millimeters, that is 0.08. And the H 250, that is 0.250 squared divided by 6. You do the calculation, I got this answer, 833.33 into 10 to the power minus 6 meters cube. Okay, right. So we got the S value. Now we know this one as well. And now it is simply a matter of substituting the numbers. So I'm going to substitute MB. MB is 50 kilonewton meter. That is 50 into 10 to the power 3. Right. And just now we found the value of section modulus is 833.33 into 10 to the power minus 6. So if you simplify this one, you get this answer. So we found the maximum bending moment, bending stress. Right? This is going to be at the outer surface, and the location is right at the top at point B here. So at this point, or at the bottom, both are the same, right? In this case, right? So knowing that this stress, if you want to design this member, now what we have to do, we need to know the material properties of this timber. So if you know the material properties of this timber, we need to make sure that the allowable material property of the timber should be less than or equal to this maximum stress that we calculated. Then this beam will not fail. Okay, so now can you see how the things that we have learned now connects with practical engineering design of beams? Right? This is what engineers do. Okay, so you do the calculation and find out the maximum internal stress. So if you know the internal stress maximum and compare with the material properties, you can find out the appropriate geometry for this member. Basically, we are finding actually section modulus. If you find the good section modulus or minimum section modulus, that will prevent the failure. That helps us to find out the good cross section for this cross sectional area to resist the bending moment. So let's bending stress. Okay, so let's let me show you how to design a prismatic beam so that it will not fail by bending. So for that, now we have just derived an equation for the maximum bending stress sigma m. It should be at the location where maximum bending moment is, and then it is m max over s. Right? This value sigma m should be less than or equal to the allowable material property, right? For a safe design, it requires the maximum stress is less than the allowable stress of the material used. So that means sigma allowable of the material, whatever the material. Now here we are using timber. If it is steel, we need to get the allowable stress of steel. You know how to find out the allowable stress, right? It is yield stress divided by a factor of safety, right? So assume that you know the allowable stress. Then now maximum stress sigma m should be less than or equal to sigma allowable for safe operation. So after simply substituting the numbers, you find that this will give me a relationship for section modulus. My section modulus of the member should be greater than or equal to this value, that is the ratio between the maximum bending moment and allowable material stress. So therefore, the minimum section modulus required come from the equal sign is this. Okay, so if you calculate this minimum section modulus, it will tell me the geometry of the cross section required. So I can select any geometrical shape that will provide minimum of the section modulus given here. Right? So that way I can design an optimum section that will resist the bending stress efficiently. Okay, right. So let's do a question in the example concept application, and that way you will understand how to do a simple design of beam. So now I'm going to show you how to design a standard cross section or decide a standard cross section for a given beam. Standard cross sections are already manufactured. When you go to market, you can buy them like I sections, L sections, H sections, right? Circular sections, hollow circular sections. there are structural steel with different shapes. So some shapes are good in supporting bending loads, some are good in supporting torsional loads. So previously in one of the lectures, I mentioned that uh, some sections are better, especially when the moment of inertia of the section is higher, is better, right? In resisting bending moment. So we need deep sections, like for example, I sections like this with the higher depth. Higher depth is much better in resisting bending loads. Okay, so that is why for most of the time beams you see that I-shaped beams. So we'll read this question. A 5-meter long simply supported steel beam AD is to carry the distributed and concentrated loads shown 20 kilonewton and 50 kilonewton. Knowing that the allowable normal stress for the grade of steel to be used is 160. So allowable stress is already given here. Sigma allowable here it is steel is 160 megapascal. Select the wide flange shape that should be used. Now this is the wide flange shape. Why it's called, this is the flange. It is wide. That is why it's called wide flange. Right. So now we know that we have to use that equation that we have just derived. Right? You don't need to memorize them. Okay. You can simply use the equation. Right. So first thing in that equation, if I go back, we can see that we need to know the maximum M. This is already given. So how to find out the maximum M? By drawing the bending moment diagram for this load distribution. Right? So let's use the new method that we have learned and develop the bending or find out the maximum bending moment faster. Okay. Okay. But before that, again, we need to first step, as a first step, we need to find out the reaction forces, right? By drawing a free body diagram. Now you understand the importance of the free body diagram. I'm kept on telling you that you need to learn how to draw it, right? So if you make any mistakes in drawing the free body diagram, you can't solve this kind of problems. Okay, let's draw the free body diagram. So I have drawn the free body diagram, and also I have constructed my shear force diagram. I'll explain to you how I constructed that. Okay, so point A here is a pin joint. Point D is free to move, is the roller support. Therefore, potentially there can be axial force and vertical force at point A. But by observation, I can say that this is 0. Okay. Then I have AY and D that I need to find out. So shall we do it first? Calculate the moment, sorry, not the moment, the axial reaction force AY and reaction force D. So we can find out the D here by taking the moment about A, sum of moment about A equal to 0. So can you write the equation quickly? So then you can see D is coming to the equation, right? D create a positive moment, therefore it is positive. D into the distance, or the total distance, 1, 1, 3, 5, right? Fine. Okay, and then 60 kilonewton create a, oh, 50 kilonewton create a downward or anti-clockwise moment, therefore negative. 50, I write everything in kilonewton. The distance is 4.4, right? 4. And distributed load, previously it is given as 20 kilonewton. So this should be 20 into the total distance is 3 meters. That is why it is 60. Okay. And then it is right at the middle, 1.5 away from the point A. So therefore it is negative 60 into 1.5. Okay, after simplifying, you get this answer. And then get the sum of forces in y direction, it is equal to 0. If I write the equation, it is ay minus 60 minus 50 and plus a d, sorry, d is 58. Okay, you simplify that one, then you get this answer. So I got the values of d and ay, and now by looking at the forces, I should be able to draw my free body diagram. Sorry, the shear force diagram, right? So at point A, shear force should be equal to the reaction force there, right? Previous experience. If you have any doubt, you can draw it a free body diagram here. You cut the member at some location and then find out the value of the shear force at point A. So it is equal to AY and it is equal to 52 kilonewton. Right. So I mark that one first, 52 kilonewton. And from A to B, distribution is load distribution is continuous, uniform distribution. Therefore, now I can find out the shear force at point B. How we can find that one? We take VB minus VA. Right? VB minus VA should be equal to negative of the area under the load curve. Negative of the area under the load curve. So this is equal to negative of area under the load curve is this total area, right? That is 60. 20 into 3, negative 60. We know that VA is equal to 52. Right? VA is 52. Therefore, VB is equal to minus 60 plus 58. So 52. 52. Right? Is equal to negative 8 kilonewton. That is how I got this answer. Okay. Right. So you mark that point here, and in between, the variation of the shear force is linear, like this. And from B to C, no other external forces. Therefore, shear force remains constant. Okay. So up to C, same shear force, negative 8. And at C, suddenly there are going to be another load, right? So can you find out the shear force just after C? We say VC plus VC plus C plus just after C. So somewhere here. Now by observation you can write that one, right? So let me write how I write it. It should be AY positive, so that is 52, right? Negative 60, negative 50. So that means negative 58 kilonewton. So that is how I got this point, right? So shear force suddenly become negative 58, and from C to D, no other forces. C up to just before D, no other forces. Therefore, same shear force. So this is the shear force diagram. Now by observation again, our target is to find out the maximum bending moment, but you don't need to draw the bending moment diagram. By observation, you can say where the maximum bending moment is. At the location of maximum bending moment, the slope of the curve, bending moment curve, should be 0, right? We previously learned that dm over dx is equal to 0. Sorry, is equal to v. So at the maximum point, v should be equal to 0. So we can see that here at point E, v is 0, shear force is 0. So the maximum bending moment going to be at E. We know the location. Okay, so that means when we can say when v equal to 0, m is equal to m max, and here we can say at point B. It's sorry, at point E, it is going to happen at point E. But we don't know exactly what E is. I did a calculation and found that E is 2.6 meters from point A. How did I get that? So for that, you can again use the same relationship that we have developed about the shear force variation. Shear force variation between 2 points is equal to negative of the area under the load curve. So let's take this distance as x. And then I can write VE minus VA as negative of area under the load curve between A and E, right? Between A to E. A to E. So what is the area? If the distance is x here, x into 20 is the area under the curve, right? Now I'm talking about this area up to this point. It is equal to negative 20 into x. Okay, now this is VE minus VA. We already know that VE is 0, right? VE is 0. VA is 52. So shall we substitute those numbers? VE is 0. VA is 52 is equal to negative 20x. From this one, we can find out x is equal to 2.6 meters. So that is how I found the value of x in here. Okay, right. So at that point, bending moment is maximum. Right. By observation, I can say that at point A, bending moment is 0. Right. So the bending moment between A and E, that is ME minus MA, is equal to the area under this curve, right? Shear force curve. So shall I write that one here? ME minus MA should be equal to the area under the curve. So area under the curve is 52. So half 2.6 into 52. So that value is equal to 67.6. I calculated that 67.6. Okay, and here MA is equal to 0. Bending moment at point A is 0. Okay, and finally my ME, which is the maximum bending moment, is equal to 67.6. So I didn't even draw the bending moment diagram. I know that maximum bending moment is at E, and then calculated the value at bending moment at ME by taking the area under the shear curve up to that point. Okay, so now the answer M max here, I have written the area under the shear curve A to E. So it is equal to half 2.6 into 52. Okay, just to complete it. So this is the maximum bending moment. Okay, so once we know the maximum bending moment, then I can use this equation with the equation I developed for minimum section modulus should be equal to M max over sigma allowable, right? So now we know that maximum bending moment is 67.6 into 10 to the power 3 and divided by the given allowable stress of the steel 160 10 to the power 6. So you do the calculation, you get this answer 422.5 into 10 to the power minus 6 in meters to the power 3, because section modulus has the three-dimensional units, three measurements, three units measured in meters. So if we converted it into millimeters to the power 3, it is equal to 422.5 into 10 to the power 3 millimeters to the power 3. So this is the minimum section modulus required from the standard section we are going to select. Okay, so standard sections of flanges like this come with some data, right? We can select those data from standard the data books. So I have uploaded one such data table in the Moodle course site. You can find that one. It's properties of rolled steel shapes like this. So it is for the wide flange sections like that, and they are identified by a designation. That designation has a W sign to indicate it is a wide flange, and then there's a number, is 840 is this height of the member. Okay, and it followed by a cross, it's just a separator. Okay, and then another number 299. This 299 is kilograms per meter. Kilograms per meter. So that means that this cross section with this designation weigh 299 kilograms per meter. Okay, and the same thing, the other information also available. If you go here, you can see that I can find out the I about the x-axis of that section. It is this much in millimeters to the power 4, and also S, this is the section modulus. Section modulus is given as 11,200 into 10 to the power 3 millimeters to the power 3. Okay, so from this section modulus, I can find now a section modulus higher than 422.5 that I have just calculated. So I have gone through all the values given and selected some sections. Okay, section shapes. These are the designate which are most appropriate for this application. So these are the shapes. They all have section modulus greater than 422.5. You can see that the lowest is 448, and then 434, and go up to 637. So which one you are going to recommend? The best standard section for this application. All are suitable, right? But we, as engineers, we always need to use less material as possible and get this job done, optimum design, right? So again, just to remind you that here in the designation, W stands for wide flange. Okay, the next three digits is the nominal depth in millimeters. This depth, I mark it as H. Okay, and the next one is the weight or the mass in kilograms per meter. Okay, so then we have to use a member which is lighter and also which can satisfy the section modulus requirement. Section modulus requirement is satisfied by all the members here, any shape. But then which one is the best by considering its mass? So we can look at from the first one, lowest section modulus is 448 and its weight mass is 46.1 kilograms per meter. So this is the first one. And next lowest section modulus is 474. And there you can see that the mass is 32.9 kilograms per meter. So which one you are going to select now? Is it this one or this one? Number 1 or 2? Number 2, right? Very obvious. So this is how engineers look at. So they find out the appropriate section and then we look at how can I do this job with as less material as possible. So number 2 is the best. So can you write the answer now? Choose, I say 2 here, right? That is W360 by 32.9 shape. Why? Because it is the lightest. It is the lightest, right? That is why the section modulus requirement is provide the minimum section modulus requirement and it is the lightest. Okay, right. So what we did in this section, we started with understanding shear force variation and bending moment variation along a beam when there are transverse loads. So we learned how to draw shear force diagram and bending moment diagram using method of section. But later we found that it is very cumbersome, very time consuming to use that method. Okay, and then we learn there's a relationship among the load applied, shear force developed, and the bending moment developed. So we learn that relationship. Using the relationship, now we can, given the load, all the loads, now we can draw the shear force diagram directly, right? And also we can draw the bending moment diagram with using the shear force diagram. But when it comes to the design, what the most important thing that we are looking at is the point where the maximum bending moment is and its magnitude. So now we know how to calculate the maximum bending moment, right? Its location and also the magnitude. With that, we can find out the maximum normal stress on the beam. Maximum normal stress going to happen at the maximum bending moment, where the maximum bending moment is, and in the outer surface of the member cross section. Okay, so using bending formula, we can find out that stress. So when it comes to design, we need to know the material properties, allowable material property. If you know that one, then we can find out the minimum section modulus required to satisfy the or avoid failure. So once you know the minimum section modulus, we can refer to standard tables and find out appropriate section. Okay, so this is the most important thing when it comes to structural design for designers when they are designing the beams. How to calculate those things, and then how to select right cross section for the application. Okay, so just to summarize what we have learned, in fact, in the industry, people use some construction rules. The rules are related to what we have learned about the relationship between the loads, shear force, and bending moment. I hope that you can understand this this chart by yourself, and the second one also yourself, right? So by using these rules, you can construct your shear force and bending moment diagrams faster. Okay, the summary I already summarized right before. So we learned the shear force and bending moment diagram to how to construct them using the method of section, and then we extend our understanding to develop it without writing any equations, right? And lastly, we learn how to design a beam. Okay, so I'm going to stop here, and we have a lot of questions in the exercises. So I'm going to do those exercises in the tutorial class on coming Monday. So come to that class online or face to face. Okay, choice is yours, and we'll see you there. Thank you.